startups. In addition, Dan has been an invited member of the U.S. White House Science and Technology for developing national R&D strategy for cybersecurity. He's also contributed to multiple presidential commissions on cybersecurity. Recently, Dan has been involved with Fields, taking the lead on a research project along with Taha Jaffer, who's in the audience tonight, on a project related to applying agentic AI to mathematical reasoning and mathematics research. So I'll give the floor to Dan.
All right. Thank you. First of all, thanks to the Fields Institute. I want to thank them for listening to a crazy guy, namely me, to get interested in AI and its applications in mathematical sciences and security. And just having the opportunity to start a collaboration and really get people from a lot of different fields and backgrounds kind of involved in something that is leading edge, but also really important for the public good. I believe that math can greatly benefit from AI, but I also believe AI can greatly benefit from math. And the reason for that is, AI systems represent kind of like the pinnacle of reasoning technologies, but math represents the pinnacle of reasoning. And the other reality is, because AI systems are becoming very complex and hard to understand, ultimately the solution to being able to govern them and secure them will come from the mathematical research community, both in the applied side and the theoretical side. And with that, I'm going to kind of jump into the topic of the day. I'm going to introduce everyone to the concept of what agentic AI systems are, what we mean by higher order reasoning systems and their applications in cybersecurity. I'm here to actually deliver some good news. The good news is there's lots of solutions in this area, and they're rapidly developing. In the work that I do in my private life, right now I'm involved in a stealth mode company that's kind of working in these areas and has been doing some research in these areas in the last 2 years. And I'm very hopeful for our future and what's to come. All right. So I'm going to give everyone kind of like a rundown on kind of key concepts, kind of backgrounds in the field. I'm trying to make this as lay term as possible, because I understand we have people here that kind of come from a lot of different types of backgrounds, but do forgive me, sometimes I am going to get a little bit technical, because I am hoping that the audience does have that appetite and interest. I'm going to talk about the ideas behind what is known as neuro-symbolic AI and what that is and why that's so important in the agentic domain. I'm going to talk about agentic planning and reasoning and executive reasoning and how that's kind of used to solve very difficult problems, especially in the cyber domain. I'm going to look at how all of these things kind of work together in modern AI integration. How do all of these elements come together? So for example, we've heard terms like generative AI, classical machine learning, and symbolic learning, and a whole bunch of things. Agentic AI is just a superset of all of those things. It's kind of bringing together the entire world of AI and essentially putting it to work and putting it to like kind of solve problems in explainable ways and to reason about problems much in the same way that humans reason about problems. And then we'll kind of get into a little bit of like what the future outlook is like and why I'm kind of hopeful about the field in general, just because of things that I've been seeing in my research. All right, so how I like to start is basically kind of discuss the fact that even in the traditional use of ML in the security field, there are challenges. And those challenges kind of stem from the fact that, and we kind of were discussing this, is a lack of explainability. So if I look at kind of the classical use of AI and machine learning in security, I'm kind of using these different types of models that I built. They're kind of doing a prediction. Examples might be, hey, I'm doing some spam detection and saying, I think this is spam with a confidence factor of like 99.1%. And that's it. I'm not going to tell you how I came to that reasoning. I'm not going to tell you how the neural net figured all that out. You just have to trust me. I'm a black box. And that kind of has its own challenges in the field. You have models that do much more sophisticated things like anomaly detection. They look at network behaviors, they look at user behaviors, and then they also come up with some scoring. But again, it's a black box, there's no explainability. And then what happens is you're kind of left to the user or the security analyst to go and figure out, okay, based on what this model is telling me, do I have actual malicious activity here or not? And in practice, having been a practitioner in this area for a long time as well, what you find is you're just chasing a lot of false positives. And you have to, that's the job, right? So your AI models, traditionally, most of them, like let's say the more sophisticated ones, they're looking at very subtle behaviors. They're generating a lot of workload for a person in what's known as in a security operations center to go out and investigate and qualify if there's a real threat or not, but they're necessary, right? Because they're looking for the types of behaviors that are not high confidence and could ultimately lead to a breach. Similarly, you also have classes of models that, as was discussed earlier, that can classify like different types of malware threats. And yes, like for things that are kind of really well known, they'll do a pretty good job of kind of convicting something. But the problem is adversarial susceptibility. The issue now is the adversaries, because they're also using AI tools, they're actually getting really good at even evading AI models for threat detection. And what they're doing is they're developing attacks which are lower and slower. What that basically means is they're not necessarily using explicit malware to achieve their objectives. They're using legitimate tooling in an environment. They're assembling an attack kind of on site. They're using legitimate tools like PowerShell or other scripting languages. They're using legitimate binaries in the environment to actually kind of assemble a type of malware attack without using malware. So because of these things, the traditional way of kind of applying ML in the field is starting to crack and it's starting to fail. And as I've just outlined, pure ML right now, it does struggle with novelty. So symbolic knowledge and agentic AI, it's exactly designed to handle this because it reasons like we reason as human defenders. So human defenders, they understand all of this. And what they do is they look at a myriad of signals. They reason over different types of logs and different types of signals and events coming from different tools and systems. And they kind of paint a picture and they really figure out and can qualify if there's a threat or not. And the promise of what agentic AI can do is exactly that. And just as I've outlined, we're kind of moving beyond classification, right? So in ML models, they're basically classifying something. They're saying, hey, I classify this as a threat or it's not a threat. I classify this as something that's anomalous or not anomalous. It requires further investigation. I classify this as this particular class of malware because of feature X, Y, Z, or I don't, right? And that's good. And within like the scope of a larger agentic system, that's still a valuable signal, but it's no longer sufficient. So agentic AI moves beyond that because it demonstrates executive reasoning. So what it actually does is it will build a plan. So for example, let's say it's like servicing an alert. It gets a particular alert from a particular security tool. On the basis of that alert, it can actually build a plan. It can contextualize. It can understand what the alert means. It can use then tools to investigate that alert, and it can decide even next steps. Does it need to do further research? Does it need to isolate? It can plan a sequence of actions, and it aims to achieve security goals, just like a human does. So this is like a little bit of an extensive chart, but bear with me. I'm just trying to summarize a lot of information here. So agentic AI and security. So the best way to think about it is autonomous AI systems. They can actually sense the environment. So sensing in this world means Well, they're collecting a lot of signal. They're collecting logs, they're collecting event information, and that's kind of allowing them to kind of contextualize or paint a picture of the environment that they're working in. It's when you kind of look at a lot of the algorithms that are going into their executive planning process or their planning and reasoning process, they're actually modeled after Markov decision processes or event-driven loops, okay? So they're making use of a lot of classical ideas that go back in AI way back, but now they're kind of coming forward because when you combine them together with neural networks and connectionist paradigms, you get like really powerful combinations happening. So when we refer to autonomous AI agents, they're able to take decisions and take actions without any user intervention. Of course, it's a user that can pre-qualify them for certain actions, but once you've allowed them to, they will merely work for hours, days, doing whatever tasking that you want them to do. So in cybersecurity, agents can investigate alerts, they can plan responses, and they can execute mitigations. That's what they're being designed to do. And the reason why they're needed, obviously, is because they can adapt, right? When you're using a classical predictive model, it's not really adapting. What it's doing is it's pattern fitting. So if it's seen a particular class of attack within its data set, it just matches that pattern. If it hasn't seen it before, or it's not close enough to what it's seeing, it'll just put up its hands and just not classify it. And so this is why agentic AI is so important in this space. So now when we talk about higher order reasoning, so AI reasoning goes about like a multi-step process. So if you've ever seen agents run, an example, like more in the consumer space, is not as advanced or sophisticated, but if you look at a lot of like the things like ChatGPT, if you look at Grok, if you look at Anthropic, they were now beginning to provide light levels of this technology. So, you know, if you've heard of DeepSeek, the reasoning steps that it takes, it actually lays out a thinking process. So it's self-reflecting, and it's saying, hey, the user is asking me to do X, Y, and Z. This is what X means. This is what Y means. This is the plan to execute this. This is what I need to research. So this technology, even in the consumer space, is already beginning to manifest. The difference here is when we're developing more enterprise class technology in this area, obviously it can do that to a much higher order level and a much deeper level, and it's being designed to also run much longer. So a reasoning cycle in an enterprise context or in higher class systems, it's no problem with it, like he's even reasoning and researching over the course of days. So in my experimentations, like it's routine for me to have an agent. I can start up an agent, I can send it away on a research task. It can go research, it can experiment, it can learn, it can self-correct, and it can come back to me 3-4 days later with a solution. In the consumer space, obviously, that's not going to happen because they're trying to service a very large and generalized audience. And if they were running something that long, you know, they would bankrupt themselves because it's even debatable if they're making profit right now on individual users. But in this world, because you can own your models and you can do things far more efficiently, you can run things longer and you can run them deeper. And then, of course, I just talk about like some specific examples, how it works to orchestrate multiple steps, how it does knowledge lookups, how it's contextualizing itself in the process, and how it's kind of combining the best of all of the paradigms. So, you know, why this all matters is because it's going to create a world for us where we basically have truly adaptable security and it's explainable. So when agents execute, they're literally telling you their reasoning process. So they're telling you what it's researching, why it's researching it. If it's using a tool on your behalf, it's telling you why it's using a tool, it's telling you what parameters it's passing into a tool. If it fails, it will tell you why it thinks it failed, and so on and so forth. We'll get to some details around how these systems are composed. And then, of course, why this is really important is all of the zero-day threats, all these APTs, all the ransomware, all of this stuff is only growing. And the reason why it's growing is because if good guys are going to take advantage of this class of technology, so are the bad guys. And we already know, we've already had a great initial session where we know that bad guys are already using generative AI, but if they actually start to use agentic AI at scale, that's going to be a far more dangerous proposition, because the type of attacks they'll be able to generate and deploy will operate at extreme velocity and at a much larger scale than what probably the industry can counter right now. But we have time. Okay, so higher order reasoning, right? What's the core concept? It's reasoning about relationships and meta level concepts, right? So when you're composing agents, when you're kind of neurosymbolically composing them, it's not that they're learning a data pattern. What they're actually learning is actual concepts. So for example, if an agent is learning about how to actually build malware, okay, it understands what malware is. It understands the concept behind it, like how it's abusing a system. It will understand how it's composed. It will understand to the level of how it makes malicious use of APIs in the operating system. What are the different types of calling patterns? How to execute a fileless attack? What are the different types of attack tools? It actually recognizes all of these entities. It understands the relationship between these entities, and it can reason over all of this. So it's not a prediction function. It's not, hey, I think I've detected like an attacker activity and that's it. No, it actually understands a sequence of all the sequences in an attack. It understands the tools that are being used. It understands how all of these ideas connect to each other, and it knows how to reason over all of it. So for example, like in a security example, I have like a really simple one here just for everyone's background so everyone can kind of appreciate it. So like first order reasoning would be, okay, if an IP is blacklisted, I'm gonna block it. That's pretty simple, right? But higher order reasoning is like something that can autonomously correlate and understand repeated failed logins and privilege attempts, and can then work to autonomously block that, or even narrow down how it's going to block it. Okay, and this is being done without like having like predetermined rules or thresholds, because bad guys can trivially navigate past those things. This is being dynamically reasoned. So when we talk about what we mean by higher order reasoning, that's like the type of benchmark that we're discussing. So, and of course, the benefits of that is that you have a system that can actually adapt to attacker strategy changes, right? So I've been involved in more live attacks than I can document, and I've seen real time, adversaries change tactics. When they're, for example, when they're doing bot attacks and credential stuffing attacks and a whole bunch of things, they're always changing tactics, always changing, how they're distributing their bots or frequencies under which they're trying something. And inevitably, if you have a system that's kind of based on static rules, they kind of game you and they figure out how to get past those rules, right? So in an agentic example, just like humans are sitting there and observing, it observes, it understands, it can detect that pattern and it can react, right? Just like we do as humans, because that's what classically happens when you're doing a defense against that type of attack. Okay. So again, another example of like what context aware reasoning is versus simple retrieval. So just on simple retrieval, when I go to ChatGPT, for example, or any other service, doesn't matter, and I'm just using an LLM and I'm putting in a query, when it's generating something, it's actually just doing a retrieval. What it's actually doing is it's going to its giant mess of weights and within its neural net, and it's just kind of predicting based on some tokens that I've given it, the type of response that I should get back, right? The example that I like to use is, what's the first word that comes to your mind when someone says peanut butter, right? But most of us will probably say jelly. Guess what? So will the neural net. And that's literally an LLM. That's literally all it's doing, is just calculating and predicting. When someone says peanut butter, chances are they want that jelly, right? And it's just putting it together. It's not reasoning about it. It's just putting it together, right? So that's the same thing when you're doing like simple retrieval. That's what it's doing. It's basically retrieving information from its neural net. And similarly, when we're looking at things within the context of, let's say, a sim, it's, when you're doing like a retrieval there, it's retrieving some information for you, but the reality is it's a human that's kind of correlating and contextualizing kind of what's going on. Just because you have an alert on your sim, it doesn't necessarily mean that you have an actual threat. Now, when you're doing context-aware reasoning, it's the AI that's dynamically correlating all the various sources. It could also be doing subsequent searches into the sim, and it can actually infer and understand real attack patterns, much like a human does, because it understands how to contextualize what's going on in the information that it's retrieving. So it's not just retrieving information, it's contextualizing it and it's understanding it, okay? And then it can, because it uses higher order reasoning, it can actually figure out pattern similarities across different types of attacks that it's seen, and it can really correlate low-level anomalies. That's another important thing too. Like in practice, what you realize is that system defenders usually only have the capacity to service critical and high-level alerts. What happens is the bad guys figure out that if I can do an attack which will only trigger a series of low alerts or medium-level alerts, the vast majority of people don't and are not able to, nor have the time to be able to understand how to write correlations for every single possible combination of low-level alert to accomplish an attack. The cool thing with the AI is that it can sit there and it can watch that day and night, and it can monitor for it, and it can build context around that, and it can understand when it's seeing very subtle attack activity. Whereas with human resources, you just don't have the capacity to do that. You don't have the capacity to go after that. Okay, so neuro-symbolic AI. Neuro-symbolic AI is really, really important in agentic systems. So it kind of it combines two things. It combines the neural paradigm, which is subsymbolic. What does that basically mean? Subsymbolic means that neural nets are black boxes. It's a connectionist paradigm. It just sees everything as numbers, and really the best way to think about it, it's just a giant complex system by the way of partial differential equations. But at the end of the day, what it's actually doing is it's doing really fancy pattern matching and prediction, okay? But it doesn't really understand. It doesn't have a symbolic understanding of what it's processing, right? And as humans, these neural nets are so big and so complex. They're billions, now going into trillions of parameters large, especially when we look at applications like LLMs. We can't possibly understand the state complexity of these machines, and how they're actually working at each state, and how they're coming to certain determinations or not. All right, but they're still very valuable when you combine them with symbolic AI, which is based on logic and rules, which is where actually AI began. This is symbolic AI is the original AI paradigm. I remember even when I was in U of T doing some courses on Prolog, which was like building AI systems using logic and logical statements and then inferring things. When you combine both of these paradigms together, things get really powerful. And the interesting thing is that LLMs, while they're at one level they are subsymbolic, they are actually able to, through LLMs, because LLMs recognize symbols, they're actually able to operate on the symbolic level. And so when you build hybrid systems which are actually combining symbolic rules, logic, and kind of encoding understandings, that way programming languages themselves are symbolic. And so when you're using LLMs and other models to kind of operate on that medium, you can begin to reason over these things. And you have a system which is inherently explainable. So for example, if I'm building a system, based on rules that an AI system is continually updating or learning from, I, as a human user, can understand those rules. I can understand that system of logic. I can formalize it. I can develop proofs around it. I can verify it. And so that's the whole idea behind neuro-symbolic systems at a high level. Okay. And then why is it important to cybersecurity? Because it gives you that hybrid-based approach, right? One, the symbolic level gives you explicit domain knowledge that you can operate on. And you can also operate on like very vast, noisy data sources, which neural nets are really good at, right? So when you combine these two things together, and then you add other algorithms and other methods and other models to elicit the type of reasoning behavior that you need, you start to get really powerful outcomes. You get the ability to basically understand novel threat activity, self-learn, and provide explainable AI, which is really important, especially in the cybersecurity field. Because whenever an agent's taking an action or whenever it's analyzing, you want it to be able to explain itself and explain what it's doing. And that also becomes the basis for how you do self-learning and further training and refinement in these systems. Okay. So why is this all important? Okay. So here's an example. At the neural level, we could be learning from data in terms of like looking at some suspicious login patterns. At the symbolic level, we can have rules, and we can have an understanding that says, hey, like a root login should never be happening from an external IP address. I know that. That's ground truth, right? And then when you can combine these things together, you have two layers that are kind of working in concert with each other to figure out is this an attack or not? Should this be something that I allow or not, right? And it basically builds mutually reinforcing confidence among your security analysts, your managers, and your system. And it basically allows you to encode security patterns into the system so that you can explain and reason over various types of complex behaviors. Okay. As opposed to, again, being strictly predictive. Again, that's a very binary thing. Either I'm predicting something or I'm not, but I'm not actually understanding activity, right? And neuro-symbolic AI is a medium which actually enables you to do that. So when we're looking at neuro-symbolic AI agents, these are kind of like the core components that make them up, okay? And there's a lot of different agentic frameworks and tools and a whole bunch of things that are now being developed in the industry. But fundamentally, these are some of the key aspects. There's one element here that I kind of take for granted. They also have short-term memory. And of course, you can encode long-term memory into their knowledge bases and knowledge graphs. Or sometimes it's just like flat files or things that you're putting in memory under a dictionary encoding. But at the end of the day, they have a way to actually ground their world in knowledge. And they have a way to reason over that knowledge, and they have a way to use tools. Now, the key thing here that I want to point out is there are standard knowledge bases and standard knowledge graphs. When we're talking about agentic systems, they can have a class of knowledge base and knowledge graph, which is internal to them because it's vectorized, right? It's using embedding. So what that basically means is that the data is in a representation that the neural net can actually understand and operate on. You can also have as external information resources, knowledge bases, and I'll get into that, and knowledge graphs that are like human readable, right? And more like traditional data stores. That's not what this is. This is vectorized. This is for the internal understanding of the AI system. And what the type of information that you put into these internal vectorized stores is what I call more steady state information. It's like, so I'll give you an example. When I'm designing an agent for the purposes of doing security research and reverse engineering, in that type of agent, the type of information I'm going to put into its knowledge base and knowledge graph is actually the practice of that field. That is the best practices. So basically, how do you actually use these tools? What's the process of reverse engineering? What are, what's the various types of assemblers and machine code? So it's like, it's the information that it represents a body of knowledge that the agent needs to operate in. So it's not temporal information, it's information which represents an entire field, okay, and an entire practice. So that's the type of information that's going to get encoded into a vector knowledge base and knowledge graph. The difference between a knowledge base, it's more linear in nature, and when you're doing quick lookups, you definitely use that tech. But when you're going to do something that requires understanding very esoteric and very deep relationships between concepts and entities, and you need to do much deeper research, or when you need to generate much more sophisticated technical content, you are always going to use vectorized knowledge graphs. And then finally, tools. Agents can use external APIs, they can use commands, they can integrate with existing tooling, and just use them much the same way a human does, and take action on those tools. They can interpret the output coming from those tools, they can reason over it, and they can take any number of actions. So when we're talking about really like professional level, enterprise grade agentic AI, this is the framework that you need to think about. And I know there's a lot of solutions that are coming out into the industry, both on the consumer side and enterprise side, but as you're kind of exposed to these technologies, it's good to have this background so you understand how to kind of frame how these systems are being built. Okay, so as I discussed, there is a difference between external knowledge graphs and the internal vectorized knowledge graph that an agent would make use of. So graph-based knowledge bases are usually just a graph DB based technology. They're used for dynamic modeling of security domains. So for example, I want to build a picture where I understand vulnerabilities that are associated to an asset. If a vulnerability is exploitable, I want to be able to support like advanced querying, multi-hop relationships. And why would I want to do that? I want the agent to be able to, for a particular environment that it's operating in, I may want it to be able to answer the question, hey, identify if server X is directly affected by exploit, if server Y is directly affected by exploit X. That's it, right? So this is a good way to basically be able to model an environment so that agent can on demand execute a query and just find that information, and then within its decision loop, take a decision in terms of what it's going to do. And then similarly with knowledge bases, when we're using them as an external information resource, this can literally be any type of data store. It really doesn't matter. But the intent there is just to have a source of current information for that's required for it to make decisions and to contextualize analysis. So in the security world, again, I might have a data store where I can query quickly for some CVEs. So that's basically like information about a specific type of vulnerability, its risk, if there's exploits for it or whatever. I may want to have a knowledge base where I have like specific types of attacker TTPs. Just that's fancy talk for essentially different types of attacks that can be done, and what are the behaviors of those attacks, how do they affect a system, and so on and so forth, and just having some facts along that. I may want to have a place where I can understand how my IT assets are configured in an environment, because again, this is important context for when an agent is going to make decisions. And this information is meant to be kept current, right? So it's temporal. It represents temporal information versus kind of more hard-to-baked information that kind of represents a knowledge base around specific domain knowledge or a specific practice or a specific body of knowledge. So that's kind of like the differentiation there. So if we bring this all together, this is basically what a typical agent will do. A human or a process could be an API triggered process. There's lots of ways to deploy this technology. It can be interactive, it could be in backend systems, it could be event based, but it's going to get an action request or a solution request. It will take that, it will go through a planning and reasoning process or loop. It will take all the facts of the request. It will build a plan and say, okay, what are the things that I need to, what are the tools that I need to use, including my internal knowledge and external knowledge. And then it will begin to execute on that plan. I use tools, it will evaluate results continuously until it's met its objectives that it's coming out of its planning and reasoning process. And that's what they do. Fundamentally, there's like a million different ways to express it, but at the end of the day, agentic technology, true agentic technology, this is the type of loop that it follows. All right. And of course, there's lots of opportunities to fine tune and train and capture experiential knowledge, even through the agent's execution process. And then there's also a lot of things that are done in agentic frameworks and agentic technologies that while they're going through this, to even provide self-correction and self-learning. So in tech that I'm working on, when an agent is, let's say, using a tool in a way that's incorrect, it will stop, it will go online, it will automatically search for information on that tool, it will ingest its entire manual, it will find the correct command and parameter, and then we'll retry again until it succeeds. And then that experience itself can be further encoded back into a knowledge graph, so it doesn't have to do that again. It will be regrounded in the facts of what it's doing. And all of this is really important for a lot of reasons. First reason is, as was mentioned earlier, LLMs and other ML tech, it can hallucinate, right? ChatGPT is probably the most, and other technologies, I'm not, just picking on them, but all LLMs are master liars. Like, they're very convincing liars. They're really, really good at it, right? And so that's why you need to have this grounding technology, because it can actually stop the hallucinations or bring it down to like really, really manageable levels. And when you have extra controls and self-correction, it's something that you can take care of. The other important thing too in agents, they're more than just LLMs. It's an ensemble of a lot of different types of models that are working together. They're increasingly multimodal. They can see, they can perceive, they can process sound. So you can think of these things as like software-based robots, right? So they have perception that works at a lot of different levels, and they can also make use of other models. And in fact, increasingly now, they can even develop models for their use. So they can literally train a model and use it within their framework. Okay. Okay, so I talked a lot about the building the plan and the execution. So here's just an example that I use for like vulnerability detection. And again, a lot of this stuff has been informed by actual research I've been doing right now in the field and actual experimentation that I've been doing. So as an example, you can do code analysis and neural scoring. You can have an ML rank some vulnerabilities by severity, by exploit patterns. You can use symbolic logic to confirm the exploitability of something. And then you can use knowledge graphs to kind of represent the vulnerabilities, their exploits, their impact on assets. And then you can have dynamic testing by an agent, where the agent can hypothesize that code might be vulnerable. It can attempt to actually exploit it to confirm it. If it confirms, it can automatically suggest fixes for known issues. And it can basically emulate the security researcher loop. So it can hypothesize, test, and remediate. They can keep on going on that. Another kind of example in this area is the bypassing of various security tools and detection methods. Again, the tech can already do similar things where it's actually coming up with novel attacks that can bypass a lot of security tools. So it's basically can reapply this pattern in many different modalities. Okay. Again, just another example here for threat detection. It's just a simple example because I'm just trying to make it approachable and understandable for as many people as possible. But an example would be like a port scanning, attempt detection. So you can really reduce false positive alerting again with using this technology. The symbolic knowledge can confirm like what are legitimate activities, right? It can give you grounding on what are expected processes or tools or systems that are in an environment. And then you can use that to minimize kind of what underlying or more primitive detector models or predictive models are kind of firing off on. And you can have a system that basically is adapting to new attack variants, and it's retaining that rule-based explainability. So it can have understanding of the environment, it can discern between what is a false positive, what is not, and then it can basically bring up your true positive rates. Because when you have these systems kind of working together, because through the symbolic side of things, you can have a true understanding of the environment and a way to reason over it. And then you can contextualize a lot of the alerting that's going to come out of like your more classical predictive models. Okay. Again, I'm just trying to explain the planning and execution process here. AI decision making, as I've been saying, it's going to follow a process which is it's going to autonomously analyze a lot of data. It's going to identify security issues. It's going to take decisions around what actions to take upon detecting those issues. And it is mimicking a human analyst's reasoning process on how it's analyzing events and how it's contextualizing them. And then it's going to use its symbolic planning algorithms to build planning around all of these things. And it's going to go through that learning, self-learning, and execution loop, as I've mentioned, to qualify if something is threat or not. And then the other important thing that I haven't gotten into yet too is now you can also build multi-agent systems. So you can have one agent, let's say, that's really specializing in doing triaging, as an example. And you can have another one that really specializes in doing DFIR or reverse engineering of threats. And then you can begin to orchestrate all of these systems. And then each agent can have its own specialized knowledge graph and knowledge base for its particular function. And again, what that does is that kind of enables you to build a much more capable system on a distributed basis than relying on a single centralized system of generalized intelligence. It actually will give you superior results and be far more resource efficient. Okay. Again, just another example here of how this stuff works together. I can probably skip over that. I think that actually this was a repeat. Sorry, I don't know why that got in there. Oh yeah, this is repeating. Sorry about that, folks. I have this thing repeated for some reason. Oh, sorry, I've been going backwards. That's why. My bad. No problem. Let me fix that. I was clicking the wrong button. Sorry. Okay. So this is just an example of what we mean by multi-agent orchestration. So you have an idea of a coordinating agent. It's like it's coordinating sub-agents. You can have one, for example, handling threat intelligence. You can have one that's handling your EDR scanning. You can have one conducting forensics. And then there's task coordination happening between them. And the one that's kind of sitting on the top is kind of acting like the SOC manager, and it's delegating to the sub-agents, right? So like very much like how human teams work, this is how agentic technology is now beginning to be built and laid out. Okay. Here's an example for doing incident response. The incident response is an incredibly difficult activity. When you're talking about human-based talent and security teams, this is kind of like On the operations side, this is like kind of pinnacle talent. There's never enough of it to go around. And making it timely is really, really important. Like making it work in a timely way is difficult, because usually when you have someone involved in incident response, what's happened is all your security tools and all of your controls have failed. And the adversary is already inside your network and they're already doing damage. And now you have to quickly respond to contain all of that. And what you find in practice is a lot of the security tools you thought are within a certain environment to help aid you in containing it, they're not. Someone didn't deploy something, a certain critical tool wasn't installed, and that's usually why the adversary's in the network and they're doing all types of damage. And then you have to figure out solutions. You got to work with just the tools that you've had. I've had scenarios where, I just have a command line. I have to go in there with a command line, remote connect into a system, and basically it's like a hand-to-hand combat over a terminal. It's not very exciting or sexy like they show in the movies, but it happens nonetheless. And this is a great area where agentic technology can be applied, because it can be imbued with all the knowledge around how to use everything within that environment, even if it's just your command line and some PowerShell. I can use that to actually do intrusion response. And indeed, in my research, I've already seen cases where it literally built PowerShell tools on demand in order to do an investigation because there were no tools in the environment. So it was able to actually, by itself, innovate and build PowerShell tools to be able to do really sophisticated, file system, process, and memory analysis, just because I took away its tools and I wanted to see what it could do. So it's already beginning to kind of exhibit these types of behaviors. Okay. This is really important too. RL means reinforcement learning. So that's basically kind of, there's different types of reinforcement learning, and that's probably an offline discussion we can have. Increasingly, a lot of the more interesting reinforcement learning that's going to happen in this world is basically going to be driven by synthetic data, and it's going to be driven by, agents are basically observing the behavior of other agents and providing kind of feedback and critical analysis, and then training underlying models on this. But within the cyber realm, you can basically run simulated environments, and you can basically emulate a whole bunch of attacks, and you can use that to generate the data that you need to then do a lot of the reinforcement learning that you want to do in the underlying models that the agent uses. So just like the best way to kind of visualize this in your mind is that just how you would train a human-based system defender or cyber defender, you can largely train agents the same way. Except the difference is you can run thousands of them at scale, and they can be doing this day and night. Key use cases for security operations, again, I've already been alluding to this. Alert triaging, I think that's like a prime use case. The reality is, when you're in a security operations center and you're a frontline analyst, you're spending most of your time chasing false positives. You're just flooded with alerts, and you're just trying to service them day and night. And so that's a great area to apply agentic technology and begin to kind of elevate, human talent beyond that. And then, of course, incident response and threat hunting. Again, the main reason why you want agents here is you want consistency and you want velocity, because time matters when you're trying to provide security after a compromise in your environment. And I talk about SOAR 2.0, again, for people in the industry. SOAR is security orchestration and automation and response. So this is like a classical way of automating in the security world, but again, it's based on route rules. So I can write up a code book to do a response, but if the adversary just changes just one element of their attack, or if they're just changing how they're executing an attack, or how long they're staying in an environment, or so on and so forth, very quickly what happens is you will be able to bypass those playbooks, or you just won't have a playbook in place to deal with an attack. So SOAR 2.0 is actually about using agentic AI so that the playbook is actually reasoned and defined on demand by the agentic AI itself. We already had an awesome talk on securing models themselves, but I just want to talk a little bit about this. I do believe that agentic AI has a lot to contribute in this area. That's because, again, it's especially when you're reasoning over things like prompts and trying to determine their intent, or you're trying to determine the intent of what an LLM is generating or has been asked to generate. This is a good area to actually apply agentic AI itself, because you can actually reason over what's going into a model, what a user is asking for a model to do, and you can reason over what a model is generating. Okay, and that's both a visual and text-based, right? Because we already have technologies like VLLMs that kind of combine reasoning together, and then again within an agentic framework, you can visually reason over what images are being generated, and what if they're malicious, or if they're you know, if there's a possible malintent there. There's a lot you can do in that area. And then there's like a lot of theorem discovery you can do to secure deep learning itself. And that's like a very interesting area in its own right that I think I would love to have a discussion with mathematicians on in general. But and this kind of like is a nice segue into the deep math program that we want to start in the institute as well. Okay, and then just another slide on securing AI itself, and just further examples of how you can put guardrails up on these systems, and again use the neuro-symbolic elements and the agentic elements to secure these systems. Okay, and also supporting audits and compliance and logging and all those good things that you want. And where I'm going to start, how I'm going to conclude is how I started. I think the future actually looks great. All of this technology, all of the possibilities that I'm seeing, it gives me actually a lot of hope in terms of the application of the technology in our field. Real world gains with this tech. Number one, you can get much higher detection rates. You can get way fewer false positives. So you can actually begin to decouple security operations centers from human labor limitations. So what that basically means is you can increase the capabilities of a security team while being able to service just way more security load, way more events. And there's going to be, I think, a new class of cyber professionals that's going to emerge as a result of all of this. And this is why I'm here. This is why I like talking to mathematicians, and I like talking to students that are going through the cyber program here in Fields. That's because I think tool use is no longer going to be a big differentiator in the field. Okay, agents and AI are going to take care of using tools, and understanding the esoteric nature of commands and parameters, and writing scripts and things of that nature. What's really going to matter is individuals that have higher order reasoning and quantitative backgrounds that can actually work in applying the tech, agentic tech in the environment, right? That's going to matter more. People that can actually train these agents, that can apply them, that can use them, that can direct them, and just have skills that are much more focused on higher order reasoning, and not necessarily route tool use, right? I think that's where the future is going to be in the field. And that's it. And I think I have time for some questions too.